Hello everybody, my name is Iman. Welcome back to my YouTube channel. Today we're going to be covering Chapter 7 for our MCAT General Chemistry playlist. This chapter is titled Thermochemistry, and we're going to cover the following objectives. Objective 1 is titled The Nature of Energy. So we're going to begin with an introduction to energy, examining its two primary forms, kinetic energy and potential energy. And while we're going to provide examples of each, our main focus is going to be on chemical energy. This is an important type of potential energy that plays a significant role in chemical reactions. Then, building on our understanding of energy, we're going to move into the second objective, where we're going to learn about the first law of thermodynamics. Now, this law asserts the conservation of energy, emphasizing that energy cannot be created or destroyed, but only transformed from one form to another. Next, we're going to explore the mechanism of energy transfer, focusing on heat and work. We're also going to differentiate between path functions and state functions here. Then we'll move into the fourth objective on temperature. So here we're going to review the concept of temperature, comparing the Celsius, Fahrenheit, and Kelvin scales. Additionally, we're going to discuss the zeroth law of thermodynamics, which lays the foundation for the definition and measurement of temperature. Then in the fifth objective, we're going to have an introduction to heat capacity. So we're going to define this concept, and then we're going to introduce a crucial equation for calculating heat. And in the next objective, we're going to continue to build on this topic by diving into enthalpy and calorimetry. We're going to cover both constant volume and constant pressure calorimetry. Then we're going to define endothermic and exothermic reactions before we learn and examine heat curves through practical problem solving. In the seventh objective, we're going to learn about phase diagrams. Specifically, we're going to learn how to read and interpret them. Key concepts that are going to revolve around our discussion of phase diagrams is going to be critical point and triple point. We're going to learn what each of these mean. Then our eighth objective is titled Hess's Law. Here we're going to explore Hess's Law, which states that the total enthalpy change for a process is the same whether it occurs in one step or multiple steps. And this principle is going to be illustrated with practical examples. Then, building on our knowledge of Hess's Law, we're going to move into Objective 9. Here, we're going to examine standard enthalpies of formation. This is going to allow us to calculate the enthalpy changes of reactions more effectively. Our 10th objective is on entropy. Here we're going to define entropy and discuss the second law of thermodynamics, which states that the total entropy of a system and its surroundings always increases in natural processes. This concept is going to be so important for understanding the directionality of energy transformations. Last, but certainly not least, we'll talk about our last objective titled Gibbs-free energy. So we're going to cover Gibbs-free energy, integrating our understanding of enthalpy, entropy, and temperature to predict the spontaneity of chemical reactions. We're also going to define and discuss endergonic versus exergonic reactions. So obviously we have a lot to cover in this chapter. Let's go ahead and just get started with Objective 1. In order for us to understand thermochemistry, we're going to need to first start by discussing energy. Energy is the essence of our very existence as individuals and as a society. The food that we eat gives us the energy to live, work, and play, just as the oil consumed by manufacturing and transportation systems power our modern industrialized civilization. And now, while the concept of energy is quite familiar, energy itself is rather difficult to define precisely. In our lecture today, we're going to define energy as the capacity to do work or to produce heat. Now, one of the most important characteristics of energy is that it is conserved. This means that energy can be converted from one form to another, but it cannot be created or destroyed. That is, the energy of the universe is constant. Now, energy can be classified as either potential energy or kinetic energy. Now, potential energy is energy due to position. Various types of potential energy include gravitational potential energy. This is energy stored by objects due to their position above Earth's surface. Elastic potential energy. This is energy stored when objects are stretched or compressed. Nuclear potential energy. This is energy contained within the bonds that hold the nucleus together. And chemical potential energy, which is energy stored in chemical bonds between atoms and molecules. Then we also have kinetic energy. Kinetic energy is energy due to the motion of the object. Various types of kinetic energy include motion kinetic energy. This is the energy of an object in motion. Sound energy, which is the energy that's carried by sound waves, which is a form of mechanical energy through a medium. Thermal energy, this is the collective energy of particles moving within a substance, contributing to its temperature. And electrical energy, this is energy carried by moving electrical charges, often electrons, through a conductor. Now, the kinetic energy of a moving object can be defined by the following equation. Kinetic energy is equal to 1/2 mv squared. M is mass, and v is velocity. Now, the unit of energy is the joule. What is the joule equal to? Well, a joule is defined as you see here. Kinetic energy is 1/2 mass. Mass can be measured in kilograms, multiplied by velocity squared. The units for velocity is meters per second, and that unit is squared. So 1 joule is equal to 1 kilogram times meters squared over seconds squared. Now, you should also be familiar with the English unit for energy, the calorie. The calorie is the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. Now, the relationship between joule and calorie is the following. 1 calorie is equal to 4.184 joules. Now, in thermodynamics, it's going to be really important to distinguish between the system and the surroundings. When we discuss reactions, we divide the universe into these two parts, the system and the surroundings. The system is the part of the universe that we wish to focus our attention on, and the surroundings include everything else in the universe. So in the case that we're looking at a reaction, we typically define the system as the reactants and products of the reaction. And we typically define the surroundings as consisting of the reaction container, the room, and anything else other than the reactants and products. In addition to the system and surroundings, we can also discuss the boundary between them. Based on their interaction with the surroundings, systems are typically classified into 3 categories: isolated systems, closed systems, and open systems. Isolated systems, these systems cannot exchange energy or matter with their surroundings. An example of this would be an insulated bomb calorimeter. We're going to discuss this later. A closed system, these systems, they can exchange energy with the surroundings, but they cannot exchange matter with the surroundings. And then last, we have an open system. These systems can exchange both energy and matter with the surroundings. So an example of this would be a pot of boiling water without a top. This kind of system is going to exchange both energy and matter with the surroundings. Now, having selected an appropriate system, our next step is then to describe the internal energy of that system. And this leads us into the second objective. The internal energy of the system represents the kinetic and potential energy of every particle in the system. Now that sounds crazy to know all of this information. Even for simple systems, this would be unachievable. But even though we may not always know the internal energy, we can usually determine how much a system changes its internal energy. Delta E represents the change in the internal energy of the system, so final minus initial. The sign of delta E tells us the direction of energy flow. If delta E is negative, then the system loses energy. And if delta E is positive, then the system gains energy. Now we can reiterate the first law of thermodynamics. This first law is also known as the law of conservation of energy. And again, it states that although energy can be converted from one form to another, it cannot be created or destroyed. Therefore, the total energy of the universe remains constant. And so we can write that the change in the internal energy of the system is going to be equal to the negative change in internal energy of the surrounding. The total energy of the universe is constant. So any energy lost by the system must be gained by the surroundings and vice versa. With that, we can now move into the third objective where we can begin to discuss how energy can even be transferred. This is where we're going to revisit how we started this lecture and redefine energy formally. Energy can be defined as the capacity to do work or to transfer heat. So we can go ahead and write the following expression. Change in energy is equal to heat plus work. Now you may also see this written as Q minus W. This kind of expression contains the same information. The difference is in how you define the signs for heat and work. We're going to stick to this expression right here, and we're going to define the signs for heat and work properly here in 1 second. But let's talk about heat and work. Heat is the flow of energy that occurs as a result of a difference in temperature. When energy is transferred as heat, the direction of energy transfer is always from hotter object to the colder object. One thing to notice is that heat is not the same as temperature. Temperature is a measure of kinetic energy of the system. Heat is a measure of the transfer of kinetic energy from one system to another. Another thing is that heat is not energy. Heat is one of two ways that energy can be transferred. Now, the second way that energy can be transferred is through work. Work is the result of a force acting through a distance. So you can write this using this expression right here. Work is equal to force multiplied by distance. Now, keeping in mind that heat and work are the two ways that we can transfer energy, let's go over our expression and how we're going to define the signs for heat and work. In chemical thermodynamics, the sign of heat and work are determined from the point of view of the system. When heat is added to the system, then heat will have a positive sign, so Q will be positive. When heat is removed from the system, then heat will have a negative sign. Q will have a negative sign. Same thing for work. When work is done on the system, or in other words, the surroundings does work on the system, then work will have a positive sign attached to it. When the system does work on the surroundings, though, then work will have a negative sign associated with it. All right, now so far we've learned about energy, work, and heat. It's going to be important for us to pause for a second now and define state functions. A state function is a property of a system that's determined by specifying the state or condition of a system. A state function is independent of the history of the system. Examples of state functions include temperature, pressure, volume, concentration, energy, enthalpy, entropy, Gibbs free energy. These are all examples of state function, which means that these variables are independent of the history of the system. It doesn't matter how you get from the start value to the end value. It just matters what the start and end value are. Heat and work are not state functions. They are path functions because these values are path dependent. So let me restate. Heat and work are involved in the process of change and thereby do not reside in the final or initial states. These two entities are known as path functions as they describe the path taken to transform from the initial to the final state. Now, having established the foundational concept of internal energy and the first law of thermodynamics, we can now explore specific thermodynamic processes that exemplify how energy and matter interact under different conditions. In thermodynamics, we often analyze how a system changes when subjected to different constraints. Four fundamental processes provide key insights into these changes. They are isothermal process, adiabatic process, isobaric process, and isochoric process. Let's go over these four fundamental processes now. Let's start with an isothermal process. An isothermal process is characterized by constant temperature. So in such a process, the temperature of the system doesn't change, meaning that any heat added to the system is precisely balanced by the work done by the system. Now, this can be visualized on a pressure versus volume diagram as a hyperbolic curve. Now, the reason for this shape is because at a constant temperature for a given amount of gas, the pressure and volume are inversely proportional. In addition, in this graph, work is represented by the area under this curve. So you can figure out the work by measuring the area underneath this curve. An example of an isothermal process is the slow compression or expansion of an ideal gas in a container that allows heat exchange with its surroundings. The system maintains thermal equilibrium with its environment, ensuring that the temperature remains constant even as the gas does work on the surroundings or has work done on it. The second process we want to talk about is adiabatic. The adiabatic process is one where no heat is exchanged with the surroundings, so the system is perfectly insulated. As a result, any change in the system's internal energy is solely due to work done by or on the system. And that's easy to understand because the change in energy is equal to heat plus work. But in an adiabatic process, there is no heat change, so Q is equal to 0. Therefore, delta E is equal to work. That means that as a result, the change in the system's internal energy is solely due to the work that is done by or on the system. Now, on a pressure versus volume diagram, an adiabatic process is represented by a curve that is steeper than that of the isothermal process. This difference occurs because without heat exchange, the temperature of the system changes as the gas expands or is compressed. For instance, when a gas expands rapidly in an insulated container, it does work on the surroundings, and this causes its internal energy and temperature to drop. On the other hand, rapid compression increases the internal energy and temperature of the gas, and this principle is evident in phenomena such as the compression stroke in an internal combustion engine or the rapid release of air from a bicycle pump. The third process we want to discuss is the isobaric process. In an isobaric process, the pressure remains constant while the volume of the system changes. So on a pressure versus volume graph for an isobaric process, you're going to see that the pressure does not vary even as the volume increases or decreases. And so you see this as a straight line like so. Now, during an isobaric process, any heat that's added to the system results in a change in the internal energy and work done at constant pressure. So a typical example is heating a gas in a piston that allows the gas to expand or contract while maintaining constant pressure. The last and final process that we want to discuss is isochoric process. An isochoric process occurs at constant volume, meaning no work is done by the system since the volume does not change. And that's because work is equal to minus P delta V. We're going to see why this is true. And so in a process where volume doesn't change, delta V is going to be 0. Therefore, work is going to be equal to 0. And so any change in internal energy is going to be due to heat. Now, this is represented by a vertical line on a pressure versus volume diagram where the volume is fixed and any change in pressure results from changes in temperature or internal energy. Again, in an isochoric process, any heat that's added to the system directly changes its internal energy, leading to a change in pressure. An example of this process is heating a gas in a rigid, non-expandable container like a sealed canister. As the gas is heated, its pressure increases because the volume cannot expand to accommodate the added energy. Now, considering these different thermodynamic processes, many of the experiments that we conduct in chemistry lab occurs in open containers under constant pressure conditions. This is called pressure volume work, and we want to begin to understand this a little bit. Let's take this movable piston as an example. By exerting a force on the piston, we can move it by a distance delta H. Since work is defined as a force applied over distance, when we compress, the surroundings are doing work on the system, and the sign of W is going to be positive. So the sign of work will be positive. Let's work through a little bit of this math so it makes more sense. Let's look at this figure right here before we do any compression. The volume of this cylinder can be described as area of the piston multiplied by the height of the cylinder. Now, if we were to exert a force on the outside of the piston, causing the gas inside the cylinder to be compressed, the change in the gas's volume can now be expressed with this equation right here. Change in volume is equal to the area of the piston multiplied by the change in the height of the cylinder. Now, keep this in mind. I'm going to redefine work for us, right? Work, we said earlier, is equal to force times distance. Now, we can also define pressure. This is something we'll go into more detail in the next chapter when we cover gases. But just really quickly here, pressure is equal to force over area. Now, if we rearrange this expression to solve for force, we would get that force equals pressure multiplied by area. Now, if we take this expression for force, pressure times area, and substitute it into our work expression, what kind of equation would we get? We would get the following equation. We can write that work is equal to pressure times area times distance. And here, the distance that the piston was moved was actually delta H. That's how we defined it. So now we can write work as pressure times area times distance, where distance is delta H. Now, A multiplied by delta H, this is just the change in volume. So now we have an expression for work that is pressure multiplied by the change in volume. We just replaced this term with volume in our expression. And now what we have here, all right, is that work is equal to pressure times change in volume. Now there's one more thing we need to do before we finish with this equation. Remember that the signs of Q, heat, and W, work, are always determined from the point of view of the system. And so in order to get the correct sign for work, with the way that we've defined work and heat, we need to apply a negative sign to this. And so really, work is going to be equal to minus pressure delta V. All right, wonderful. The negative sign is needed because work will always have a sign opposite of that to delta V. Now, if a gas was to expand, you would know that delta V is going to be positive. Your gas is expanding, so your change in volume is going to be positive, and that's going to result in your work having a negative sign. If your gas contracts, delta V is going to be negative because your volume is getting smaller, and the sign that would be associated with work here in this scenario is positive. So if a gas expands, remember the system does work on the surroundings, delta V is positive, W is negative. If the gas contracts, the surroundings do work on the system, delta V is negative, W is positive. The last thing in this section that we should know is the following conversion. 101.3 joules is equal to 1 liter times atmosphere. This might come in handy later on, but it's just an important conversion to commit to memory for the MCAT. Wonderful. Now that we've finished up this section, we can move on to our fourth objective, which is going to be a discussion on temperature. Temperature is a fundamental concept in thermodynamics that quantifies the average kinetic energy of particles within a substance. This energy is directly related to the motion of particles. So at higher temperatures, particles move faster, while at lower temperatures, their movement slows down. Now, we've talked about temperature previously, especially in our Chapter 0 video, but today we want to do a quick review on the different scales that we discussed earlier: Celsius, Fahrenheit, and Kelvin. Now, the Celsius scale is widely used in most of the world for everyday temperature measurement and scientific work. It's based on the phase changes of water, with 0 degrees Celsius being the freezing point of water and 100 degrees Celsius being the boiling point. Now, to convert temperatures from Celsius to Fahrenheit, the formula that you would use is the following. Fahrenheit equals 9/5 multiplied by Celsius plus 32. So that's how you convert temperatures from Celsius to Fahrenheit. Now, the Fahrenheit scale, this is primarily used in the United States for non-scientific temperature measurement. On this scale, water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. The conversion between Fahrenheit to Celsius is the following. 5/9 multiplied by, in parentheses, Fahrenheit minus 32. This is how you would convert from Fahrenheit to Celsius. Then our last scale that we're going to talk about is the Kelvin scale. This is the standard unit of temperature in the International System of Units, the SI units, and it's used extensively in scientific research. The Kelvin scale, it starts at absolute 0. All right, this is 0 Kelvin. This is the point at which particles theoretically stop moving entirely. Absolute 0 is going to be equivalent to minus 273.15 degrees Celsius. Temperatures in Kelvin, they can be converted to Celsius using this formula. You would take your Celsius degrees and add 273.15 to it. All right, now that we've refreshed on that, let's learn about the zeroth law of thermodynamics. The zeroth law of thermodynamics provides a foundation for the concept of temperature. It asserts that if two systems are in thermal equilibrium with a third system, they are also in thermal equilibrium with each other. This law implies that temperature is a fundamental and measurable property that can be used to determine the thermal equilibrium state of multiple systems. So the visual representation of this law is that we have, say, system A, B, and C. All right. When in thermal equilibrium, we can say that A and B are in thermal equilibrium. All right. And A and C are in thermal equilibrium. And according to the 0th law of thermodynamics, that would mean that systems B and C are also in thermal equilibrium. So in summary, understanding temperature and its measurement across different scales is really crucial for studying thermodynamic processes. And the 0th law of thermodynamics really underpins our ability to measure and compare temperatures. Now, our next objective is heat capacity, but we're going to continue that discussion in the next video. I hope that this first part was super helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.